All right, hello everyone. In this supplemental lecture, what I'd like to do is present some extra descriptions on linearization, give an example on an inverted pendulum, and then go into stability, which is the last topic of Chapter 1. The reason I'm doing this supplemental lecture is just to give you a bit more material to understand the linearization process better, which should be helpful for homework 1 and will be helpful for studying for your midterm and even beyond. So without further ado, let's get started. So in linearization, we start by first considering a dynamical system that is of the form x dot equals f of x comma u. That is the state equation, which I'll denote by equation 1. And then we have an output equation, y equals h of x comma u. Now in this setup, we have a nonlinear system. And ultimately, what we would like to do is to approximate this nonlinear system by a linear system. And the reason we want to do that is because it turns out that the number of tools that we have available to us to do analysis, control, estimation, optimization is very large with linear systems. If our system is nonlinear, as shown in equations 1 and 2 here, it turns out that the set of tools available to us drops dramatically. So that really motivates the question, can we approximate our system as linear and then use some of the tools that are available to us? So that's the motivation, and this is how it goes. So we have this nonlinear dynamical system, and I also want us to consider some equilibrium points. I'm going to denote the state, control, and output by xeq, ueq, and yeq respectively. Let me emphasize here that these are just numbers. They're constants, all right? And because they're equilibria, they satisfy the set equations here, which essentially says when I plug in xeq and ueq into f, then it spits back 0. That is, the state stops moving when the state and control are equal to xeq and ueq respectively. We can also compute a corresponding output at equilibrium, which is the value of h when I plug in xeq and ueq, and we'll denote that value by yeq. Let me emphasize here that yeq need not be 0. That is, when the states stop moving, that doesn't necessarily mean that the output is 0. Okay, so then let's now formulate the problem statement of linearization. So our goal here is to approximate the dynamics in equations 1 and 2 by a linearized system specifically around these equilibrium points xeq, ueq, and yeq. Okay, so that's the goal. And the key tool that we're going to use to execute linearization is Taylor series. So here on this next slide, I would like us to recall the Taylor series approximation. So imagine that we have this function f, right? And it has arguments x1, x2, all the way to xn. So there's n arguments here. And what we'd like to do is to approximate this nonlinear function f with respect to its arguments around some nominal values. So x1, x2, all the way to xn. We're going to approximate f around the respective values x1 naught, x2 naught, all the way to xn naught. Now for shorthand notation, I'm going to call the entire vector of x1 through xn x. And the point in which we're linearizing around, I'm going to call that by x superscript 0. Okay? So then what the Taylor series expansion says is we can approximate f of x1, x2, all the way to xn using a Taylor series approximation, which goes as follows. So first, if we're approximating f around x1 all the way to xn equal to x naught, then the first term here is actually going to be the 0th order approximation, which is to just take this function and evaluate it at x equals x naught. Okay? And it turns out that that's going to be the 0th order term of our Taylor series approximation, and we have more terms. So the first order terms are going to involve some derivatives, and because we have multiple arguments here, that is x1 to xn, we need to take the derivative of f with respect to each one of these arguments. So for example, let's start with x1. The first order term in the Taylor series expansion is going to be partial f by partial x1, and then all the arguments here, evaluated at x equals x naught times x1 minus the point we're linearizing around, x1 naught. Okay? And then similarly, we'll do the same for we'll do the same for x2. That is, I'll take the partial derivative of f with respect to x2. Evaluate it at x equals x naught, and then multiply that by x2 minus x2 naught. All right, and then we'll do that for all the remaining terms all the way up to the nth argument, xn, which has the exact same form here. Okay, now all of these terms here comprise the first order terms. Then beyond this, we're going to have higher order terms. I'll just use the acronym HOT, higher order terms here. That'll be second, third, so on and so forth here. And the point is that we want to, with the Taylor series approximation, we're approximating this nonlinear function f by a power series in x. So the first term that's shown here is the 0th order term, and you can see that there's no variable x here after we evaluate f. And so because of that, it's the 0th order monomial, the polynomial term in this power series expansion. The next set of terms here we call the first order terms because you can see that these derivatives, after we evaluate them at the nominal point x naught, get multiplied by xi minus xi naught, and this is linear in the xi's. Okay, so these are first order terms because they're linear in the x's. Then beyond that, we can have higher order terms that will involve x to the power 2, x to the power 3, etc., etc., etc. So the utility of Taylor series expansion for linearization is that we're going to truncate the Taylor series approximation right after the first order terms and use that as a way to approximate the dynamics. So let's now jump into applying Taylor series to our dynamics. So what I want to do now is apply Taylor series up to first order terms, because those are the linear ones, to the nonlinear dynamics, namely 1 and 2, around the equilibrium. Namely, if we go back to this first slide here, we have equation 1 and 2. Let's focus on equation 1 for a moment. What we're going to do is approximate this nonlinear function f by a truncated Taylor series approximation, truncated up to the first order. So let's just go ahead and do that. So here I'm going to rewrite the beginning of equation 1, which goes like x dot of t equals, and now what I'd like to do is approximate f of x comma u with this Taylor series approximation. So this is how it goes. First, we're just going to take f and evaluate it at the equilibrium values, that is xeq and ueq, okay? And that's the 0th order term. And then we have two arguments, x and u, so then the first order terms are going to involve partial derivatives with respect to x and partial derivatives with respect to u. So let's go ahead and write that. Partial f partial x evaluated at x equals xeq, u equals ueq, and then this will be multiplied by x, remember this is a function of time, minus xeq. And then similarly for u, so this will be partial f partial u. And all of this is just going to be evaluated at the equilibrium. And then multiplied by u minus ueq. Okay? And technically speaking, see if I can find an eraser here. This is not equal, right? Because it's an approximation. It is an approximation here, okay? All right, now what I'd like to do at this point is actually make a few definitions that are going to help us out. So I'd like to define A to be this partial derivative, also known as a Jacobian of f with respect to x, evaluated at the equilibrium points. And similarly, I'm going to define B to be the Jacobian with respect to u. Now, although I'm writing all this notation, these derivatives evaluated at these equilibrium points, in the end, A and B are just matrices or vectors with elements that are comprised of constant values. Okay, so they're just numbers. They are just numbers. All right, now with that definition, I can rewrite my approximation here, x dot of t, to be approximately equal to first we have the 0th order term, so I'm just going to plug in my values of x and u at the equilibrium values, and then we have a times x minus xeq, okay, and then b times u minus ueq. Okay, very good. So we're almost there. Now, let's make a few observations. So the first observation I want to make is on the first term on the right-hand side here. Now, this equals 0 by definition. Why? Well, when I take f and plug in xeq and ueq, this equals 0 because that's how we define xeq and ueq. Let's return to this first slide here. We said that we want to consider these equilibrium, xeq, ueq, where when we plug xeq and ueq into f, it just spits out 0. So by construction of the equilibrium values here, this 0th order term just goes away. It disappears and becomes 0. Now next, I want to make some definitions for these differences here. So I'm going to define this quantity that we're going to call x tilde to be x minus xeq. And then similarly, we're going to define u tilde to be the difference between u and ueq. So what's going on here is if we plot the equilibrium value of x and u, and it happens to be here, all we're doing is translating the coordinate system such that the equilibrium values are at the origin of this transform coordinate system denoted by x tilde and u tilde. So that's all that's happening there. Now, the utility of doing that is so we can arrive at this next slide, where I can now have a nice clean expression for the Taylor series approximation, which looks like x tilde dot equals ax tilde plus b u tilde. Okay, so all I did was I got rid of the zeroth order term. I then rewrote x minus xeq as x tilde and u minus ueq as u tilde. Now, note on the left-hand side we had x dot. What I did here is I wrote x tilde dot y. Well, note that they are one and the same, because if I look at the derivative of x tilde, that is by definition of x tilde going to be equal to x dot minus x eq dot. Now, because x stops changing at the equilibrium value, stops changing quite literally means that the time derivative is 0. So x tilde dot and x dot are one and the same. So now we arrive at this linearized system, x tilde dot equals ax tilde plus b u tilde, which is our approximation of the original nonlinear system, equation 1 here, around the equilibrium points. Okay? So this really closes out the linearization process. Note that the linear system is fully characterized by these matrices or vectors, A and B, which are given by these expressions. Specifically, A and B are the Jacobians of f with respect to x and u, respectively, evaluated at the equilibrium points. So linearizing, ultimately at the end of the day, is just a matter of differentiating f and evaluating at the equilibrium point that you're linearizing about. It is that simple. Okay, so now I'd like to just give you a sketch of what repeating this for equation 2 looks like, which is this output equation, y equals h of x comma u. Okay, so when we apply the Taylor series approximation truncated at the first order terms, what we're going to get is this zero orderth term, right, where I just plug in xeq and ueq into h. And then the first order terms are there will be two of them, one with respect to x, evaluated at the equilibrium, and then finally a second term here, which is the Jacobian with respect to u evaluated at the equilibrium. Okay, and I'm actually missing something here. This should be times x minus x eq, and this is times u minus ueq. Now, similarly, we're going to define the C and D matrices, which are going to be these Jacobian terms. Okay. And then we're also going to use the same definition of x tilde and u tilde. So now when I rewrite this with the notation that I've just defined, we will get the 0th order term plus c times x tilde of t plus d times u tilde of t. Okay, now there's an important distinction with respect, well, compared to the state equation, and it's the following. If I look at the 0th order term, h evaluated at xeq and ueq, it in general is not 0. In fact, if we go back to the definition of the equilibrium, h evaluated at xeq and ueq is going to be yeq. It's just the equilibrium measured output. So this is going to be yeq. Okay? Now, noting that that's the equilibrium output value, if I flip that to the left-hand side, okay, which then means this goes to 0, then this quantity here, I would like to define to be y tilde. That is the difference between y and its equilibrium value. Once I do that, I then arrive at the final output equation, which looks like y tilde equals cx tilde plus d u tilde. So as you can see, the left-hand side is a bit different than the state equation. We actually need to subtract off the 0th order term, combine it with y, and then use that to define y tilde. And voila, we have our linearized output equation, which is fully characterized by these matrices C and D, which similarly are just the Jacobians of h this time with respect to x for C, with respect to u for D. Okay, very good. All right, so next, let's do an example. It's a very famous example when learning about linearization and stability, and it's known as the inverted pendulum. So here's the setup. I want you to imagine that we have this pendulum that's composed of this mass, and it's connected to a pivot by some massless rod. And we're going to assume that the length of this rod is given by L. Now, because this pendulum exists on Earth, it is subject to a gravitational force given by m times the acceleration of gravity, the constant g. And I'm keenly interested in the angle of this pendulum. So I'm going to denote by theta, which generally evolves in time, the angle of the pendulum with respect to the vertical. Okay? Now, I'm also going to imagine here that we have some sort of motor at the pivot, like a servo motor. And this motor can enact a torque, which I'm going to denote by tau, which will cause the pendulum to move in clockwise or counterclockwise direction, depending on how I actuate this torque. Okay, now this might seem like a complete arbitrary textbook example designed to teach theoretical concepts, and that is true. But it turns out that this particular example has a very close and important and timely energy application. So I want to go into my browser here and actually talk for a minute about floating wind turbines. So something that's very interesting about the wind resource is that there is a tremendous amount of wind offshore. Now, to access this wind, you might install a wind turbine. Now, most of the wind resources exist at depths that are beyond 50 meters. So your options are basically to design some sort of structure that goes from the surface of the water all the way down to the seabed, which could be 50 meters deep or beyond, or you could make it floating. Now, if you affix this to the seabed and it's deeper than 50 meters, then you can imagine that there's this immense amount of steel that you need to install and pour down. And by some estimates, this could actually result in 60, 70, 80% of the total capital cost. Just the steel to affix this thing into the seabed. The other option for doing deep sea offshore wind is to make these turbines floating. Now, what's interesting about these turbines is that the blades here have a heavy mass, and what we would like is to make the rest of the structure as light as possible. So essentially what you have is a big mass up on top, and you want the rest of the mass to be as small as possible. So it's essentially an inverted pendulum. And of course, what we would like to do is if we had a way to actuate torque here right at the sea surface as the waves are undulating up and down, we would like to maintain this wind turbine in a vertical position such that it can capture as much wind energy as possible. So although I've got this goofy example of this inverted pendulum, which may seem like a textbook example, it is actually the perfect archetype to begin thinking about how do we control deep sea offshore wind. Okay, so if you want, you can think about that energy application as we move forward. Now what we need to do is to derive the equations of motion for this. And to do so, you will basically just need to consider Newton's second law, but in angular coordinates, where the angular speed of the pendulum here times the rotational inertia is going to be equal to the sum of torques acting on the bob here. So if you go through the process of, for example, creating a free body diagram and summing the forces and equating that to the rotational inertia times the angular acceleration, then you'll find that the rotational inertia is going to be given by ml squared, and the angular acceleration is the double time derivative of theta. And then there will be two torques acting on the bob here, namely gravity, the component of gravity that is orthogonal to the pendulum arm here, and then also the torque acting on the motor. So if you work that through, then projecting gravity onto the coordinate that's orthogonal to the pendulum arm, you'll see that torque is going to be given by mg times a moment arm L sine theta. Okay, that's the projection. And that is going to push theta in an increasing direction. And similarly, we also have torque, which is acting to in the same direction as gravity here. Okay, so these are the equations of motion, which is essentially an exercise in mechanics to derive. Now next, I would like to define my state variables, and I'm going to define x1 to be the angular position theta, x2 to be the derivative of the angular position, also known as angular speed, and then my control input, u, is just going to be the servo motor torque that I'm going to use to try to keep my deep sea offshore wind turbine straight up in the air. So when I do that, I can then derive the state space model as follows. So x1 dot is theta dot, which is just the definition of x2. And then x2 dot is theta double dot, which is just this equation of motion with both sides divided by ml squared. So dividing both sides by ml squared, we get g over L times sine of x1 of t plus 1 over ml squared u of t. Okay, so now we have our state space model. And let me also just clarify that this first state equation, the right-hand side is going to be F1. That is, it's going to be the dynamics corresponding to the state x1. And the second one we're going to denote by x2, F2, which is going to be the dynamics of x2, the angular speed. And I'm using this notation F1 and F2 because that'll be useful when we take derivatives later on. So the first thing to do will be to compute the equilibrium at some nominal angle, x1 EQ, that I'm interested in. So because we're keenly interested in keeping this offshore wind turbine upright, I would like to compute what the equilibrium values are when theta equals 0. And theta is just x1. So this is x1 EQ equals 0. Okay, now to do this, there's two parts. Well, we're just going to set the time derivatives to 0. Sorry, it looks like I have an error here. This should be no dot. Okay, so the first state equation here, I'm going to set to 0 and then evaluate the right-hand side at its equilibrium value. So immediately I get x2 EQ equals 0. Very good. And then the second state equation right here, I'm interested in when x2 dot is 0, it stops moving. And then I'm just going to evaluate the right-hand side at the equilibrium value. Okay, now x1 EQ equals 0. So this eventually becomes sine of 0. Now the sine of 0 is just 0. So this goes away, which leaves us with the second term. Now for this equation to hold true, we need that UEQ equals 0. So the equilibrium eventually becomes, well, 0 for everything. So all the states are 0, and it turns out that the motor torque should also be 0. All right. Very good. So next, what we're going to do is to linearize the dynamics. Let me call this the state space model. State space model, dynamics, they're one and the same. Around the equilibrium values, which is just the triple x1, x2, u being equal to 0, 0, 0. Okay. Now note in these equations of motion, the first equation is actually linear. All we have on the right-hand side is x2. The second state equation, the one for x2, it turns out that this is nonlinear because we have the sine of x1. The sine function is not a linear function, so therefore that breaks linearity of the entire system. So really this is the problematic one, and the one for which we would like to see what happens to it when we go through the linearization process. Okay, so first let's focus on the first state equation. So x1 dot, and we're just going to do the Taylor series truncated to the first order term. So I'm going to take f1, evaluate it at these equilibrium values, 0, 0, 0. That's the 0th order term. Then I would like to take the derivative with respect to x1. I'm going to evaluate that at the equilibrium values and multiply that by x1 minus x1 EQ. And similarly, we have the derivative with respect to x2. And finally, the derivative of f1 with respect to u. All right. Now, if we walk through this carefully, when we evaluate f1 at these equilibrium points, it's going to be equal to 0 by definition of the equilibrium points. Now, f1, the derivative with respect to x1, well, if we go back here, we'll see that f1 actually doesn't depend on x1 at all. It doesn't even show up. So when we take this derivative, it is just going to be 0. Even before we evaluate it, it's just 0. f1, its derivative with respect to x2, well, we have x2 that shows up here in a linear way, so the derivative is quite simply 1. And then the derivative of f1 with respect to u is going to be 0 because u doesn't even show up in f1. Okay, so this is just 0. All right, so what we're left with in the end is actually just this term, x2 minus x2 EQ, which you know eventually we're going to define as x2 tilde. Okay, so the first state equation was linear in the first place, so nothing interesting was going to happen. We should essentially get out the same equation. The second state equation will be more interesting because we have this nonlinear sine term. So now let's focus on the second state equation. So I'd like to approximate x2 dot using a Taylor series. So first I'll evaluate f2 at its equilibrium. And then I'm just going to repeat exactly what I have above, but f2 instead of f1. Okay. So now it's just bookkeeping, rewriting the equation above, but with f2 instead of f1. We don't have to think very hard here. Just a matter of copying down these terms. I could probably fit that. Well, this will eventually be u tilde. Okay. So the 0th order term here will be 0 by definition of the equilibrium. The derivative of f2 with respect to x1, let's look at that. All right, so we're focusing now on this term here. Okay, so the derivative of this with respect to x1 is going to be g over L cosine x1. g over L cosine x1, and then we're going to evaluate it at 0. And just to be formal and complete, all these variables are evaluated at 0. Okay, very good. Now we have x2 with respect to f2 with respect to x2. So actually f2 does not depend on x2 at all. x2 doesn't even show up in this equation, so that's going to be 0. f2, the derivative with respect to u, is just going to be the coefficient here, 1 over the quantity ml squared. Okay, so this is just 0. And then we have 1 over ml squared times u minus u equilibrium. Okay, very good. So now if I clean all this up, what I eventually get is, well, let's now focus on evaluating cosine x1 at x1 equals 0. The cosine of 0 is just 1. So in the end, what we're going to get is g over L times x1 tilde plus 1 over ml squared u tilde. And then going back to the first state equation, this is just x2 tilde. So now, if we summarize and clean up, in the end, what we're going to get is x1 tilde dot is just equal to x2 tilde, and then x2 tilde dot is equal to g over L times x1 tilde plus 1 over ml squared u tilde. Now note in the first state equation, we don't have any coefficient for x1 or u. In the second state equation, we don't have any coefficient for x2. But most importantly, what we now see is that we have a linear set of state equations, a linearized set of state equations, all in terms of these perturbation variables, x1 tilde, x2 tilde, and u tilde. So now for our inverted pendulum problem, I can now write the linearized system in matrix vector form as follows. So the states are x1 tilde and x2 tilde. And we have its time derivative on the left-hand side. Then we're going to have some A matrix, which will be 2 by 2, multiplying the vector of states x1 tilde and x2 tilde. And then a 2 by 1 matrix, that will be the B matrix, multiplying u tilde. Now all we have to do is look back to these state equations and fill out the coefficients. So we just have x2 tilde, so there'll be zeros for all the coefficients except the one corresponding to x2. So the first row will be 0, 1, 0. And then the second state equation, we have g over L with respect as a coefficient to x1 tilde, and the 1 over ml squared as a coefficient to u tilde. Okay, and then in the end, this is the A matrix, and this is the B matrix, and we are done. That's it. We have now linearized the inverted pendulum around this equilibrium point that is the inverted pendulum in the vertical position. So now I want to take a moment to discuss stability. Just make a few comments that'll be helpful. So what is stability? Now in this class, a lot of students are very interested in optimization. How do we minimize some costs or maximize some sort of utility or reward in some sense? Stability is actually a much more fundamental concept. Something that is a simpler and more modest objective than optimization, okay? And it's just asking the question, does the system blow up? At the very least, we do not want the system to blow up. And what do I mean by blow up? So specifically, stability is an analysis that tells us if xt blows up or stays bounded, which means the following mathematically. So blowing up would mean that xt, the state vector, goes to infinity. Possibly, yeah, as time marches forward. Now that we call unstable. That is bad news, bears. We do not want to engineer our systems so that the states go to infinity, because that typically means something dangerous happens. Now, an alternative would be that the entire state vector goes to 0. That's very nice. Everything just stays calm, and as time goes to infinity, everything settles down to 0, which could be some nominal value, some nominal state. Okay, so that we call asymptotic stability. Now there's actually an alternative, something in between going to infinity and going to 0, and that's that x stays finite. That is, it doesn't go to infinity, but it doesn't go to 0. And this situation we're going to refer to as marginal stability. Marginal stability. Okay. Now, because we're modeling these systems by ordinary differential equations, one way you could check this is by directly solving the differential equations. When you directly solve it, you'll get the trajectory for x, and you could just look at the solution and see, does it go to infinity as time marches forward? Does it asymptotically converge to 0 as time marches forward? Or does it do neither of those things? It might oscillate around some value or converge to a constant finite but non-zero value. In that case, we call it, in that last case, we call it marginal stability. So you could solve the differential equations, but it turns out there's actually a really clean test for which you do not have to solve differential equations. And this is super clean and easy to remember. It's so easy that you really do not have to remember much about solving differential equations if ultimately your goal is checking stability of linear systems. So first, let me remind you about eigenvalues, because that's the key mathematical object in the stability test. So let's denote lambda sub I, where I is just an index from 1 to n, to be eigenvalues of system matrix A. Now, this system matrix A is an n by n square matrix, and this comes from our linear dynamics. Okay, something that looks like x dot equals ax plus bu. So it's this one, this coefficient, this matrix coefficient on x. It turns out that the eigenvalues of A, lambda sub I, it turns out that properties of these eigenvalues fully characterize stability of this linear system. Super clean, easy to remember. It's quite phenomenal that all we have to do is check eigenvalues of A, and that'll tell us everything we need to know about stability of this linear system. So here's how it works. I'm going to list some conditions, and you check if these conditions are true. And each condition is going to correspond to some conclusion. Okay? So the first one is the following. Where should we start here? Yeah. So we're going to check just the real part of this eigenvalue lambda I. And if it's negative for all the indices, okay, 1 to n, that is lambda 1, lambda 2, all the way to lambda 3, if we check the real part and it's strictly less than 0, then the conclusion here is that the system is asymptotically stable. In other words, you compute the eigenvalues of A, there will be n of them. It turns out that those eigenvalues are possibly complex numbers. So in the complex number, there's a real part and an imaginary part. Just focus on the real part. If the real part, if the real parts of all the eigenvalues are all strictly negative, then we have asymptotic stability. That's the first condition. The second condition is a slight relaxation of this. That is, if the real part of the eigenvalues is less than or equal to 0 for all I 1 to n, then this corresponds to marginal stability. In other words, think of this as the following. Is if condition 2 holds, what that ultimately, and condition 1 does not, then what that ultimately means is that there is some index, or some lambda I, where its real part is equal to 0. So all it takes is one of these eigenvalues to have a real part that is exactly 0, and then we get marginal stability. If the real parts are all strictly negative, it's asymptotically stable. And then the third condition is basically not any of the above, which means that the real part of the eigenvalue is strictly positive for some I, not all of them, but just any one, for some I. If any one of them has a positive real part, then the conclusion, unstable. Your system blows up. One or more of the states will go to infinity. Okay? So let's actually do an example here, and this will be the last one. So this will be inverted pendulum return. And in our inverted pendulum example, when we linearized it with respect to the vertical position, it turned out that the A matrix was 0, 1, G over L, 0. Okay, so now I want to ask the following question. We imagine that this inverted pendulum is in the upright position, that is theta equals 0. What I would like to know is when the inverted pendulum is in the upright position, is it asymptotically stable? Is it marginally stable? Or is it unstable? Now, intuitively, if you think about it, what stability means is if I'm at the equilibrium and I perturb it ever so slightly, okay, I just slightly tap it, or there's the tiniest gust of wind that acts on it, stability would mean that it's robust to that perturbation and it'll return back to the vertical position. Okay. Now, if it's unstable, what that means is that it'll basically go away from that equilibrium position. The states will keep increasing away from it. Now, intuitively, you would imagine that for a pendulum in an upright position, if I slightly tap it, it actually is going to fall down. So intuitively, you might imagine it's not stable. So let's see if the conditions return back what intuition says. So what I need to do is to compute the eigenvalues of A. Now you may remember from linear algebra that computing the eigenvalues of A involves something called a characteristic polynomial, which comes from defining this. So it's the determinant of lambda I minus A, where I is the identity matrix. In this case, it's just 2 by 2. And what I want to do is solve this equation for lambda. In the end, this is just some nonlinear equation with respect to lambda. So the determinant of lambda I minus A is going to be the determinant of the matrix lambda minus 1 minus G over L, and then lambda, that equal to 0. And then when I take the determinant, that's just going to be lambda squared minus the off-diagonal components. Okay. And if I just clean this up a bit, what I get is lambda squared minus G over L equals 0. Now this is a difference of 2 squares. So it turns out that lambda is actually, well, I have 2 eigenvalues, lambda 1 and lambda 2, is going to be plus or minus the square root of GL. Okay? Now, the real part of, say, lambda 1, say the positive one, well, I mean, these are both just real numbers. There's not even an imaginary part. So the real part is actually just plus G over L. Now, this is greater than 0, which means it's unstable. Okay, that is when we tap the inverted pendulum in the upright position, it's actually going to go unstable. That is, the states are going to go away from that equilibrium value. And as far as the linearized approximation is concerned, it seems to just keep going until infinity. Now, just as a mental exercise, I'm not really going to write too much down here. Suppose that instead of linearizing this pendulum around theta equals 0, I linearize it not with respect to the vertical position, but I linearize it with respect to the downward position. That is theta equals pi radians, or 180 degrees. Now, in this downward position, we expect that if we perturb it slightly, then it won't go drastically away from that equilibrium point. So you can check for yourself that if we were to linearize around x1 eq equals pi, then it turns out that the A matrix, I'll leave this to you as an exercise to check for yourself, will be almost the same, but G over L becomes minus G over L. Now, when you do that, then it turns out that the characteristic polynomial looks like lambda squared plus G over L equals 0, which actually means that lambda 1 and lambda 2 are equal to the imaginary number j, actually plus minus the imaginary number j times the square root of G over L. Okay, j is the imaginary number. Okay, which is just the square root of minus 1. Okay, you may have seen this as I. In electrical engineering, they use J because they don't want to confuse with electric current. I'm going to use that convention because it's just the way I learned it. So, anyways, here the eigenvalue is a complex number. It turns out that 0 is the real part, and then we have plus minus j times square root of G over L. So there's just a complex part. So the real part of both lambda 1 and lambda 2 in this case is actually 0. So therefore, we're actually going to conclude marginal stability. Right? So that's a different conclusion than the one we had for the inverted pendulum in the upward position. All right, so with that, that concludes this modular online video to give you just a bit of extra material on how to do linearization and stability analysis. To review again, linearization is the process of approximating a nonlinear dynamical system like the one shown here by a linearized system. In the end, what we find is that our linearized system is characterized by A, B, C, and D, and A, B, C, and D are basically given by the Jacobians of f and the output function h with respect to x and u, and that's essentially it. Now, one thing I also want to clarify is that in the notes and in lecture, I actually defined the perturbation variables first, and then did the Taylor series approximation. What you notice here is that I actually did the Taylor series approximation first before ever talking about the perturbation variables, and I just followed that through. Okay, and it wasn't until we got all the way to the end here that I defined x minus xeq and u minus eq as these perturbation variables. Another reason that I'm doing this online video is to show you that you can actually reverse the steps with respect to what I had in the notes and also in lecture, and you get the same result. And after teaching this over many years, what I found is probably this version of linearization is a lot more intuitive to students. So I really hope that is helpful to you. So that's the end of this lecture, and thanks for listening.